In this video, we will explore the focusing parts of the eye, the cornea, iris, and lens. Hello, my name is Craig Blackwell. I'm an ophthalmologist in Santa Cruz, California. In other videos, we have concentrated on disorders of the eye, like glaucoma and macular degeneration. This is the first of two videos in which we are just going to explore how the eye works, because it is a very interesting subject on its own. In this first video, we will explore the focusing parts of the eye, the cornea, iris, and lens. In the second part, we will cover the parts that record the image, the retina, optic nerve, and brain. Remember, this is for your information, and if you have eye problems, does not replace consultation with your ophthalmologist. Light is all around us, bouncing off objects in random directions. The eye gathers in those random light rays and focuses them in a sharp image on the retina. So the eye is usually likened to a camera, but really it is more like a video camera, constantly registering new images and transmitting that information in the form of nerve impulses to the brain. The brain receives nerve impulses and assembles them into an image, and then of course the brain has to make sense of what it sees. Let's start off by getting oriented to the eyeball. Starting from the front, the cornea is the clear window that lets light into the eye. The iris is the colored part. In the middle of the iris is an opening called the pupil. That controls how much light gets into the back of the eye. Behind the iris is the lens, which focuses light like the lens of a camera. Lining the inside of the eye is the retina, which senses the light and turns that into nerve impulses, which are carried along the optic nerve to the brain. On average, the eyeball is about 24 millimeters long from the front of the cornea to the back of the sclera. You can see the cornea is more curved than the rest of the eyeball. Here's what the parts actually look like. In this view of the front of the eye, the cornea is clear, so it is seen only by the reflections from the surface. The iris is the colored part, and the pupil is the opening in the center of the iris. This is the view we get through the microscope we use to examine the eye. In this picture, the pupil is widely dilated. The beam of light is coming from the left, passing first through the cornea and then the lens. I've outlined each of these with the dashed lines. This is the lens of a middle-aged person. Looking through the dilated pupil, this is the view of the inside of the eye. The head of the optic nerve is right of center, with veins and arteries spreading out from there. The retina lines the entire inside of the eye. Here it appears as the orange-colored background. We will now look at all of these parts in detail, starting from the front. The first thing that light encounters as it reaches your eye is the tear film on the surface of the cornea. If the tear film is smooth and even, say glassy, this is the first step in making a clear image. If it is not smooth, then light is scattered and vision is reduced. This is a significant issue for people with dry eye. Tears are mostly saline, but also contain electrolytes, antibacterial proteins, and other things that are important for the health of the cornea. The tear film has three layers. A mucus layer on the surface of the cornea that allows the watery part to spread out over the cornea. Then there is a middle watery layer, and on the external surface an oil layer helps prevent evaporation. The oil comes from glands in the eyelids. The middle watery layer comes from the lacrimal gland located under the upper brow. Tears descend over the surface of the eye, swept over by the eyelids. The tears exit through two little drainage ducts which carry them into the upper part of the nasal cavity, which is why, when you cry or your eye waters, that your nose runs. So the tear film is more important than you thought. The cornea is the clear window that lets light into your eye. By clear, that means it transmits more than 99% of the light that falls on it. The cornea also does most of the job of focusing light entering your eye. Of the 60 units of focusing power necessary to focus light on the retina, 40 units, or 2/3, comes from the curvature of the cornea. The average cornea is about 12 millimeters in diameter. In the center, it is a 0.5 millimeter in thickness. Looking at the cornea in a little more detail, the diagram shows there are three layers: a surface skin layer, a middle structural layer, and an inner layer. This is what the layers look like as seen through a microscope. Now, consider that the cornea and sclera are formed from the same tissue as your skin. While the sclera is opaque like skin, how is it that the cornea can be so clear? It has to do with two things. First, even though the cells are similar to skin, in the cornea they don't fill up with opaque keratin. Second, the very consistent alignment of cells and fibers that make up the cornea allows light to pass through like through a crystal. The surface layer of the cornea, called the epithelium, is the eye's first line of defense against the outside world. It is about 5 to 7 cells thick. Just like your skin, new cells are constantly growing from the base of this layer, and the old ones are being shed from the surface. A new surface layer grows in about 1 to 2 weeks. When you get a scratch, what we call a corneal abrasion, the surface layer is usually the part that is scraped off. Fortunately, a healthy cornea heals rapidly. For a small abrasion, new cells often grow to cover a defect in 24 to 48 hours. The middle layer, called the stroma, is the structural layer. It maintains the shape of the cornea. While we're on the subject, let us talk about a term that causes a lot of confusion: astigmatism. A perfect cornea would be evenly round like a basketball. Some people have that shape, but most have some degree of ovalness, meaning that the cornea is shaped more like a football, which means light entering on the steep axis is not focused at the same place as light entering on the flat axis. That makes an unclear image, a problem usually corrected by your glasses. To be complete, it is also possible that your lens may not be perfectly round, and astigmatism may come from there as well. The inner layer of the cornea, called the endothelium, is composed of a single layer of cells that act as a pump to keep excess fluid out of the cornea, which is necessary to keep it clear. If the pumps can't keep up, then fluid builds up in the cornea, and that makes vision cloudy. The term for fluid buildup in the cornea, or any tissue, is edema. If the cornea is like the crystal of a watch and the iris is like the face of a watch, you can picture there is a space in between, which is called the anterior chamber. That space is filled with watery fluid called aqueous humor. The aqueous fluid is produced by the ciliary body just behind the iris. It carries oxygen and nutrients the inside of the eye needs to function. Consider that neither the cornea nor the lens have their own blood vessels, so they mostly depend on this fluid for their nutrition. The aqueous is pumped into the eye, circulates around the lens, through the anterior chamber, and exits through a filtering system located where the iris and cornea meet. The filtering system is called the trabecular meshwork. Through the early decades of life, this system of fluid going in and out is in balance. It keeps the eye inflated with a pressure of about 16 millimeters of mercury. In later decades, the filtering system doesn't work as well, which makes it harder for fluid to exit the eye, and that makes the pressure go up. If the pressure goes up high enough, it can damage the optic nerve, causing loss of vision. That is what glaucoma is. The main function of the iris is to regulate the amount of light entering the eye, which it does by varying the size of the pupil. But there is also something to be said for the beauty of its color and at close view the intricate details. It turns out that no two irises are alike, and so the iris can be scanned as a means of identification, as unique as a fingerprint. The same is also true for the blood vessels of the retina. Structurally, the iris has two layers. You can see in this microscope view the back layer is heavily pigmented. The front layer, called the stroma, is composed of loose connective tissue with embedded blood vessels and muscles. The amount of pigment in this layer determines the iris color. Here is a simple way to think about iris color. If the front layer of the iris has no pigment, the iris appears blue. What you are seeing is a scattering of light from the black pigment background, like the blue color of the sky. In this iris, there is just a little pigment around the pupil. In the iris, the melanin pigment has an orange-brown color. If it is scattered on the surface, the iris appears light green. Moderate coverage of pigment gives a greener color. Full coverage makes a brown color. And there can be patches of darker brown pigment as well as nevi, which must be watched like a mole on your skin. Pupil size is controlled by two sets of muscles. One goes around the pupil. When it contracts, it makes the pupil smaller. The other set is radial. When it contracts, it pulls the pupil more open. These two sets of muscles act in balance to control pupil size. Besides light and dark, there are a number of factors that affect pupil size. For example, when you are relaxed, the pupil is relatively smaller. When you are stressed enough to produce adrenaline, part of the fight or flight response, the pupil dilates. Behind the iris is the lens, like the lens in a camera. It is responsible for 1/3 of the focusing power of the eye. The big advantage of the lens is that it can change focus, allowing you to focus both at distance and at near, at least until you reach your 40s. The focusing muscles of the eye are located in the ciliary body, which forms a ring around the inside front behind the iris. It is attached to the equator of the lens by thin filaments called the zonules. When you want to read or work up close, there are several actions that happen simultaneously to make that happen. The eyes converge, the lenses change focus, and the pupils constrict. All this is necessary to focus at near. For the moment, we will discuss the lens changing focus. The geometry is a little tricky, and this is separate from any glasses prescription you may have. When the focusing muscles are relaxed, the lens is flatter. That is your distance focus, say for driving. When you want to focus up close, like for reading, the ciliary muscles contract, the lens becomes rounder, which bends light more and brings near focus. This all works wonderfully well for a while, but as time goes by, the lens gradually but steadily loses its flexibility. The graph shows how the lens becomes less flexible over time, making it more difficult to change focus, no matter how hard the muscles are working. That is why everyone over age 40 who is not nearsighted ends up needing reading glasses. The other big thing that happens to the lens with time is that it gradually changes color and gets cloudy. If it gets cloudy enough to interfere with vision, we call that a cataract. This picture shows a totally opaque lens, the extreme level of cataract. The cataract in this picture is more typical. The lens shows overall yellowing and cloudy spokes, which is a moderate cataract. Everyone has some degree of these lens changes with time, but not everyone gets to the point of needing cataract surgery, which is removal of the cloudy lens and replacement with a new artificial lens. If you do need cataract surgery, know that the technology to do it has gotten really good. The retina is a layer of nerve tissue lining the inside of the eye. It receives light and makes an image like film in a camera. In Part 2, we explore the parts that create the image, starting with the retina, with its rods and cones, then the optic nerve, and the brain.